Okay, das ist der Punkt. Okay, so good afternoon. If you're the last speaker in a session like this, of course, you have no idea what the previous speakers will say, and so there may be some overlap or not, we'll see. And I actually realized that some of the slides were already included in Christoph's beautiful talk, so I will go through them quickly, and that will also allow us to come to a conclusion somewhat faster. I've titled my talk, Life Above the Hagedorn Temperature, Quark-Gluon Plasma at SPS, RHIC and LHC, because obviously the Hagedorn concept of hadron thermodynamics led immediately to the question is there life beyond that at temperatures above TH? As already Jan mentioned in his introductory remarks, 1965 was quite a momentous year in terms of physics. It saw the discovery, the experimental discovery of the cosmic microwave background and the first publication of the idea of an exponential hadronic mass spectrum. Now, what was not immediately apparent is that these two observables and these two observations, or these two theoretical and experimental concepts, were very closely connected and opened up a challenge, namely, if the universe was hot in the beginning, did it ever attain temperatures that are higher than the Hagedorn temperature? And if so, what filled the universe at that time? Now, in the 50 years since then, physics and astronomy and astrophysics have made unimaginable progress. From the crude observation of the existence of a black body radiation, we now have data from WMAP and Planck in particular that deduce precision determinations of the cosmological parameters simply from the measurements of the fluctuations in the background radiation. And we've been able to do experiments that probe the question of what lies beyond the Hagedorn temperature to a detail that at that time were not even conceivable. If you want to make real progress in physics and approach very difficult questions, then all people here who climb mountains know that to reach the summit you need three things. You need good equipment, you need a sound strategy, and you need determination. And in the study of hot and dense QCD matter, that means a number of things. You need high luminosity colliders that can produce hot QCD matter at a rate so that you can measure precisely sophisticated observables. You need large acceptance, high data acquisition rate detectors with good particle ID so that you know exactly what you're measuring. On the theoretical side, you need realistic lattice QCD for the thermodynamic quantities. And as Christoph has shown you, we are now there, finally. You need realistic transport codes that can connect the thermodynamics to final observables in a realistic way. You need dynamical models that allow you to explore both the physics of weakly coupled and strongly coupled quantum field theories. And we have those now also, at least in certain limits. And you need to be able to do a comparison between these models and the data in a multidimensional, multivariate way in order to eliminate the uncertainties that come immediately, the model dependencies that come if you only compare one observable. So after several decades of experimental and theoretical development, all these necessary tools are now in place, and the field can make the progress towards final determinations of the physics that we all hoped for decades ago. On the one hand, the relativistic heavy ion collider at Brookhaven, which is 3.8 kilometers long, has really opened up the field to a precision study of QCD matter beyond the Hagedorn temperature. And there were originally 4 detectors, and 2 are remaining, Phoenix and Star, that do the measurements. On the other hand, we have the Large Hadron Collider that opens up the highest energies and matter at the highest temperatures with 3 outstanding detectors that do fantastic phenomenal measurements. So first I wanted to talk about the QCD equation of state. Much of this actually was already covered by Christoph, but let me go through some aspects of this. The equation of state of matter has 2 contributions. One is what we normally call the equation of state, the conservative part of matter at complete thermal equilibrium and statically existing, which is governed by an energy density and a pressure. But then, if the matter is actually flowing, as it does in a heavy ion collision, you also have dissipative contributions, which in lowest order are encoded in 2 parameters, namely the shear viscosity and the bulk viscosity. It turns out that if the term from the bulk viscosity that corresponds to the expansion or the compression of matter becomes too large and exceeds the one from the conservative pressure, the matter becomes unstable and cavitates. And it's an interesting question whether this is an effect that we actually see in heavy ion collisions. I think that is still an open question and needs to be further investigated. But in general, the energy momentum tensor of matter in a realistic situation is one that relaxes to this quasi-equilibrium value dynamically on a time scale that itself is related to these viscosities. In QCD matter, we believe that time scale is very short, less than a Fermi over C, but it is not negligible. Also, while the shear viscosity has a lower quantum bound, that simply comes from the fact that there is an uncertainty relation that does not allow matter to relax arbitrarily fast. There is no such bound on the bulk viscosity. Actually, as a matter of fact, if matter is conformally invariant, the bulk viscosity is exactly 0. So the QCD equation of state now has been mapped at least at 0 chemical potential with great precision. We know it better theoretically than we can hope to measure it experimentally. And so for most of the calculations that are done nowadays, these theoretical values, these functions of energy density, pressure, entropy density, speed of sound as a function of temperature are taken as input. But you can also relax them and ask the question, how well do the experiments agree with this? And this has been done recently, and it turns out that actually, if you assume that the thermodynamic behavior is quite different, the experiments tell you, no, it is very close to this. So it is very consistent with the experimental data. We know from the calculations where the so-called critical, quasi-critical temperature is, where chiral symmetry gets broken or restored depending on from which direction you go, and it's a range of about 150 MeV, and the energy density is rather low. It's less than half a GeV per Fermi cubed. Christoph talked about the hadronic mass spectrum and its relation to QCD, to lattice QCD. I don't want to go through this. Indeed, what he showed is that you need additional resonances that are not in the particle data booklet to have agreement with the data. And it turns out that you need to include resonance up to about 2.5 or 3 GeV to have agreement. So there is life beyond the particle data booklet. That's what we know now from lattice calculations. It would certainly be interesting and an experimental challenge to find out what the structure of these resonances is. We have to include such resonances. Higher states are not in the particle data booklet, also to compare with the experimental data. And so, for example, here in this work from the Brookhaven-Bielefeld-Wuhan collaboration, you find that if you look at the ratios of particles, baryons in particular, emitted in heavy ion collisions, in order to get a consistent fit with temperatures in the mid-150 MeV range, you have to include a large set of baryon resonances that are not in the book. We're also making considerable progress in the direction of calculating the equation of state at non-zero baryon chemical potential. That's still a big challenge. There has been quite a bit of progress by using Taylor expansions or analytical continuations in terms of the baryon chemical potential, but we're clearly approaching the point where we can explore the phase diagram also on the lattice into the baryon dense regime, although not as far as we would like at this point. As Christoph has pointed out, we now are able to actually explore the phase boundary of QCD using the data. And this is in fact true because the two machines that are now in operation, RHIC and LHC, produce matter in the range that is around the phase boundary. If you ask the question, what is the energy or the temperature range covered by RHIC, it goes from here around 140 MeV up to about 300, 350 MeV. The LHC extends to 400, maybe a little higher. And this is just the range in the equation of state of QCD where the transition from a Hadron gas into a perturbative Quark-Gluon plasma happens. So this is machines that cover just the right range of temperatures. Let me skip this here because Christoph has already skipped through this and come now to talking about the Quark-Gluon plasma itself. That is matter beyond the Hagedorn temperature, or more precisely, beyond the critical temperature of QCD, which is in 150 MeV range. If we want to explore it, we have to first ask the question, what are the quantities that we can reasonably explore? What are the quantities that are physically well-defined and can be related to observables? And there's obviously the equation of state, energy density, pressure, entropy density, and so forth. And these are related to quantities like spectra, collective flow, and fluctuations. We have the non-equilibrium properties, dissipative properties like the shear viscosity, also the bulk viscosity, but also transport phenomena that have to do with the diffusion and momentum, and actually the shear viscosity is also related to diffusion of momentum. These are very hard to calculate on the lattice because they're dynamical quantities, but experimentally they are actually quite readily accessible because they correspond to the anisotropic collective flow and the energy loss of partons in the matter. Another quantity that's hard for lattice to calculate is its ability, the ability of the Quark-Gluon plasma to emit electromagnetic radiation, lepton pairs, for example. This can be seen in lepton pairs and photons, but again, because it's a dynamical quantity, it's hard to calculate on the lattice, although it is considerably easier than the momentum transport properties. And finally, another easy calculable quantity is color screening length, that is the screening of color fields above the deconfinement transition. But it is much more difficult to calculate, to relate the observable quantities to, because it turns out there are a multitude of phenomena that contribute to the suppression of Quarkonium states, which is the best way of looking at the color screening. So the surprise and the real discovery in looking at matter beyond the critical temperature was to find that it is actually matter that has the properties of a very easily flowing fluid, also called the perfect fluid. And here we connect the energy momentum tensor, including its dissipative contributions, to hydrodynamics by the conservation law of energy and momentum, with the hydrodynamic equations that also contain the relaxation time with which the energy momentum tensor relaxes to the quasi-equilibrium value with the conservative and the dissipative contributions. The interesting quantity in here on the dissipative side is the shear viscosity or the bulk viscosity divided by epsilon plus p, the enthalpy, or the entropy density to make a dimensionless quantity. And this is the kinematic shear viscosity, kinematic viscosity in the case of shear, eta over the density. In the case of a relativistic fluid, eta over the entropy density. The way it's measured is, as you know, elliptic flow, or generally anisotropic flow, where you look at the anisotropic flow components that are related to the anisotropies of the pressure in a non-round, in a deformed region of hot matter. And this is actually very much related to what is happening and what is used in the case of the early universe, the black body radiation, because we are not only seeing the average deformations, but we see in fact the event by event fluctuations of the density in which energy is deposited. And so in each event, we have a multitude of these flow coefficients. It turns out that this flow that is generated through the initially anisotropic energy density is very sensitive on that quantity of the shear viscosity of the entropy density. And as this simulation here by Schenker and collaborator shows, the data clearly distinguish between no shear viscosity, a minimal quantum bound of the shear viscosity, or twice that. Now, where on these curves the data fall depends to some extent on the assumptions about the initial state. And so modeling the initial state has become very important. It turns out that if you not only look at the elliptic flow, but also at higher flow components like B3 and B4, this becomes more sensitive. And so you can actually use the data themselves to some extent constrain the initial energy density fluctuations. And I'll come back to that in a moment. So depending on different values that you use, you can get different results. But it also depends on the energy at which you probe the matter. And you find that, for example, if you do the same analysis for the higher energy data at the LHC and those at RHIC, you get somewhat different values for this ratio. But they're not tremendously different. They show that in both cases, you're not very far away from the quantum bound, which is 0.08. So this is indeed a very liquid form of matter with an extraordinarily low shear viscosity. This is a plot that is contained in a PhysRep letter that was just accepted and is coming out in the next few days. It shows data from RHIC measured by STAR in gold-gold and uranium-uranium collisions. And the different aspect of uranium-uranium collisions is because uranium is a strongly deformed nucleus, you can, by looking at the fluctuations in the multiplicity, select events that are either belly on belly like this or tip on tip. In the tip on tip collisions, you have a larger longitudinal length of colliding matter, and therefore you get higher multiplicities. And when you look at the elliptic flow velocity that you get, the elliptic flow parameter, you find that whereas in gold it is roughly independent of this because actually there is not such a geometric effect or a very small one. In the case of uranium, it's a very strong one. And you can now ask the question, to what extent are different models of the initial density fluctuations in agreement with what you see? And it turns out that if you use a model that is based on a Glauber approach to nucleon-nucleon collisions, it really deviates from the data. There's no way to get in agreement. You cannot dial a shear viscosity parameter that agrees with the data. On the other hand, if you assume that the energy density fluctuations in the initial state are dependent on partonic interactions, either by using a model in which you use Glauber but based on constituent quarks, of which you have 3 in each nucleon, or by using a model in which it is actually based on interactions among gluons contained in the nucleons, you get a reasonably good description. Actually, it turns out that the constituent quark Glauber model works best. So this indicates that not only are we seeing a very liquid form of matter, but also we begin to understand what the origins of the density fluctuations in the initial state is. How far can we push this? Whereas what we've done here up to now is look at a single observable and compared it with the simulations. What a group of people led by Stefan Bass at Duke has done is to take a large number of observables, just in the same way as the blackbody radiation analyzers have used multiple observables to determine a number of different cosmological parameters. So what I've used is data from ATLAS and from ALICE on various quantities in terms of particle spectra, flow parameters, but also the fluctuations in the flow velocities of V2, V3, and V4 in order to compare with calculations that are based on simulations of the collision through an initial state deposition, through hydrodynamics of the Quark-Gluon Plasma phase, and then hadronic breakup using a hadronic cascade model. And they varied the various parameters in the simulation and compared with a multitude of these observables. And so you can go and look at their contribution to quark matter, and you find that you get very good fits to particle spectra, to the mean PT of particles, to flow cumulants, and so forth. And then you can ask the question, to what extent does that constrain individual observables? And the two most interesting ones are, from what I've said so far, are the shear viscosity and the bulk viscosity. And it turns out that both are actually sensitive. And you get a number of different results for the shear viscosity, depending on whether you assume that it's constant independent of temperature or whether it allows to vary as a function of temperature, but it constrains that variation. And in the range of about 200 MeV, there is agreement from these data from the LHC that the shear viscosity has to be between about 0.08 and 0.13. So this is now constrained on the basis of multiple observables. You could do that better if you would do the analysis not just for one beam energy, but for multiple beam energies. And the new run will certainly help, but this also needs to be extended to RHIC data. You also find that you get a substantial contribution from the shear viscosity, from the bulk viscosity near the critical temperature. Of course, that assumes a certain analytical form of the bulk viscosity as a function of temperature, but it leaves the absolute magnitude free. And so this is the first determination that bulk viscosity is actually important in comparison with the data, and it has a reasonable value. So here they have put together a similar analysis of the allowed regions of parameters similar to the cosmological parameter fitting group. This, I think, is clearly the future, and more data will help to constrain these dependencies much better. Another interesting question that we can ask is, how small can a Quark-Gluon plasma be? Now, it turns out that if the matter is strongly coupled and approximately conformally invariant, then can one make a case that actually the size doesn't really matter. This doesn't mean necessarily that hydrodynamics applies for an arbitrary number, rapidity density, that is an arbitrary size of the system, but it suggests that the transport is independent of the size of the fireball, which is not completely surprising, but interesting to see if you have matter that has a certain scaling dependence. What about the data? And here we have recently seen data from RHIC, where they have looked at proton nucleus collisions deuteron nucleus collisions and helium-3 nucleon collisions. They're quite different in the initial shape of the state that is, of the matter that is created. Typically, in deuteron collisions, you find states that are elongated in an elliptical form, whereas in the case of helium-3, on average, you get a stronger triangular contribution. The calculations were determined to describe the Duron goal data, and what the surprising result is that if you look at proton or on helium-3 goal data, you find that the agreement is astoundingly good. So these were theoretical predictions, and they strongly argue that indeed, even in these small collisions, you produce matter that has the same properties as you do in a large nuclear collision. So this, again, I think is a surprise. It is not totally surprising in the sense that matter that has such a low shear viscosity is strongly coupled and has what would correspond in a kinetic theory to a very short mean free path. So hydrodynamics should apply even to small sizes, but nonetheless, it is something that even a few years ago, few people would have believed. Let me next say a few words about the chemistry. And of course, Trischow already did that to some extent. One of the arguments from the very beginning, as Jan pointed out in his remarks, was that looking at strange quarks is a good way of actually determining the dynamics of the confinement. And the idea is that simply if you have deconfined quarks, strange quark-antiquark pairs are relatively easy to produce and quick to produce. And simulations, calculations indicated that actually you need gluons in your matter in order to make that happen at a time scale that is relevant for equilibration heavy ion collisions. So I think it is fair to say that in the 30 years since those original days, various theoretical studies have shown that the liberation of quark and gluon degrees of freedom is required for the equilibration of strangeness to be dynamically achieved. And the observations at the SPS, at RHIC, and at the LHC have clearly shown that strangeness equilibration is attained in the big systems and at the highest energies. These were the original measurements by NA57. Quark and collaborators showed that there is strong enhancement of strange and multi-strange baryons. These are similar measurements from RHIC. Again, very strong enhancement with strangeness is seen. These are the star data. And finally, we have remarkable data coming from the LHC measured by Alice, which have measured this in great extent now as a function of the size of the system, as a function of the particle multiplicity in the final state. And while they show that the equilibrium, thermodynamic equilibrium in the Hadron gas is fully reached in the big systems, they also see that as you go to smaller and smaller systems, the equilibrium is not reached, at least not the grand canonical equilibrium. So the question is now, what makes the smaller system contain less strangeness than you would expect in a grand canonical ensemble? Of course, as Christoph pointed out, in a small system, you would expect that strangeness conservation plays an important role. So you should not simply forget about the fact that overall the system has to be strangeness neutral. And here is a comparison of these data for various strange baryons, lambda, psi, and omega baryons, as a function of the system size. This is divided by the pion yield. And you see that if you make a specific assumption about the correlation radius over which strangeness is neutralized, you can get a semi-good fit of the data. It doesn't prove that this is the reason. There is another possible reason, and that is simply it takes time for strangeness to equilibrate. because you have to have reactions to produce strange quarks and antiquark pairs. And so in addition to a conservation effect by a finite correlation volume, you can also have a suppression effect due simply to the time that you didn't have time to reach the equilibrium. And I think it will be very interesting in the next few years to make detailed studies of this, to what extent this suppression effect for small systems is due to strangeness conservation and to what extent it is due to finite reaction times. There's another way you can actually use hadron chemistry to look at the question of how hadrons are produced. Are they produced from a Quark-Gluon plasma, or are they produced from some form of hadronic matter? And that makes use of the fact that the matter flows. And it flows anisotropically. And because the anisotropic flow can either be generated in the quark phase for individual quarks, or because it could be generated in a hadronic phase, it turns out that it has a different effects on meson and baryons, because mesons contain a quark-antiquark pair, whereas baryons contain three quarks. And so fundamentally, baryons are more sensitive to the flow because each quark constituent contributes to the anisotropy. This was recognized early on in the RHIC data, where it was found that if you look at the anisotropic parameter V2, for low transverse momenta, baryons have less anisotropy than the mesons. But then if you go to high momenta, mesons show less anisotropy than baryons. This is naturally explained if you have this effect. And so the mass splitting down here is a property of hydrodynamics. You simply see less of an effect of anisotropic flow for particles that are massive than for particles that are light. Whereas up here, the failure of hydrodynamics to actually describe the data can tell us how hadrons are formed from quarks. And the suggestion, as you know, was that you could actually rescale the curves measured for hadrons in terms of the curves for quarks by realizing that if mesons are made out of quark-antiquark pair, then their anisotropy parameter should be related to those of quarks at half the momentum on average, although it's a little bit more complicated when we go into details, whereas those for baryons should be related to the quarks of a third of the momentum, but 3 times as large because each quark contributes. And so this suggested a rescaling of these curves by valence quarks, and indeed when this was done, this was in excellent agreement with the data. And in the meantime, there are many more data from RHIC and also from the LHC that give a pretty good confirmation of this, although at the LHC you see small but definitive deviations, something that I believe is not surprising because there is still generation of anisotropic flow in the late hadronic phase. So this symmetry should be somewhat broken, and it is. Finally, let me say a few words about the 2 other observables that I talked about, namely those that have to do with momentum dissipation and color screening, which relate to color screening and color opacity. Color opacity is, of course, related to the quenching of jets as a fast hadron goes through the matter. And here we have tremendous amounts of data from the LHC and from RHIC now that show that jet quenching. And it was recently analyzed and published last year by the JET collaboration, which actually used the data to determine the quantity that describes that longitudinal momentum loss, the so-called jet quenching parameter Q hat, which was determined with an accuracy of about 30%, both at RHIC and the LHC. Again, it shows that the matter at RHIC is slightly more effective relative to its density in quenching momentum, corresponding to a somewhat lower shear viscosity than at the LHC. And it will be interesting to see with the next set of data and the next set of analysis how far we can push that analysis and how it can also be included in the multi-parameter analysis that was shown you before. We've clearly seen the suppression of germanium states that Helmut Satz and his collaborators predicted 30 years ago or so. And it's turned out to be a more complicated phenomenon because in addition to color screening, you have effects like quark ionization in the hot medium, but you can also have recombination of quarks and antiquarks if you produce enough heavy quarks, like charm quarks at the LHC. And this is still an actively developing field. Theoretically, models have been constructed that actually can describe the data, but it is still, I think, somewhat at the point where we have not been able yet to determine to some precision what the color screening length is, but with a bit more work, we may actually get there. And these beautiful data from CMS here, for example, with resolved Upsilon states and germanium states, clearly show that there is a big difference in the suppression of Upsilon 2s and the germanium ground state, although they are very similar in size and binding energy, and this clearly points to the recombination mechanism, as do other measurements, both at RHIC and the LHC. What is missing here is a resolved measurement of the Upsilon states at RHIC to do a full comparison with the LHC measurements, and I hope we will get there. So because I'm biased, I'm at Brookhaven, I'm particularly interested of RHIC. Let me say a few more words at the end towards the future of RHIC. We've worked on this over the past few years, and we've proposed to the nuclear physics community in the US that we should complete the scientific mission of RHIC in 3 campaigns. The first campaign really looking at the heavy flavor states, in particular open charm hadrons, but also open B hadrons. Have a second campaign after installing low energy electron cooling to do precision measurements into the baryon-rich side of the QCD phase diagram, so that we can measure observables that are really sensitive to potentially the presence of a critical point. And finally, install a new detector called s-Phoenix that will do precision measurements of jets and Upsilon suppression, and also some other quantities maybe, and before we shut RHIC eventually down. So this is now encoded in the long-range plan that was just approved last month, and we're hopeful that we can actually complete that program. In the case of the beam energy scan, the goal is to look at the phase diagram here in the baryon-rich domain and to see if we can find and identify possible signals of a critical point in terms of critical fluctuations. There is a rather model-independent scenario that says that a quantity that's related to the kurtosis of the baryon fluctuations should change sign as you go through the critical point or along the critical region. You don't have to exactly hit the critical point for that. You just have to go from this region over to the region in which you have a first-order phase transition, where that quantity relative to its Poisson value should change sign. And in order to measure that, you need a detector that has sufficient range and rapidity, and you have to have enough statistics in your data sample in order to measure the change as a function of beam energy, so you can clearly identify either a positive or a negative sign of that quantity. And these are the data here that were measured in the first beam energy scan. You see they are with big error bars. They do indicate the possibility of sign change, but if you really want to do this, you need the data that we expect in the second beam energy scan. If there's a critical point, we should be able to find it. Of course, it may not be there, but then we could show that it is not seen. The s-Phoenix detector is, as I mentioned, there to measure in precision jets, resolved jets, and Upsilon states. And the idea here is to use the fact that the Upsilon states at a given temperature and a given resolution scale lie in the on the thermal side of the scale within the length scale in the matter, whereas jets with their initial point-like formation can probe the structure of the matter at subthermal length scales. And so in principle, if you can measure both of these quantities in precision, and you can compare data from RHIC and the LHC, you should be able to actually, with some still not precisely known accuracy, but fundamentally qualitatively, resolve the different structure of QCD matter, the Quark-Gluon plasma, on the thermal length scale versus the subthermal length scale. This is really what ultimately can tell us, hopefully, whether matter, how you have a transformation from quarks and gluons at the microscopic scale to something that looks like a perfect liquid. The precision that we expect with RHIC's luminosity on all these measurements is quite impressive, and it should complement the LHC data that are going to be taken in the next few years during run 2 of the LHC. So let me conclude with a general remark. What we've learned is that beyond the Hagedorn temperature, or more precisely, and Christoph is right, not beyond the Hagedorn temperature, but beyond the critical temperature, lies the liquid Quark-Gluon plasma. This is a remarkable discovery by any measure. Because if you imagine that you start out with a liquid form of matter, namely nuclear matter, and you heat it to about 100 billion degrees, it turns into a gas. It turns into vapor. And when you then heat it further by another factor of 20 to 2 trillion degrees, it suddenly becomes again a liquid. I think this is something that is quite unique in condensed matter physics. And it is not only a liquid, it is actually, by the best way of measuring the liquid properties of a substance, namely the shear viscosity over entropy ratio, the most perfect liquid that was ever observed. And still, in spite of attempts to produce similar states of matter with better quantities in the laboratory in atomic traps, the Quark-Gluon plasma, with the limits on 8 over S that we now have, is the best liquid that we know. And it is a fundamental theoretical and experimental quantity to find out how this is possible. How can matter have these quite remarkable properties? In many respects, it's still a mystery. But I'm confident that the precise study of hard probes on various scales at RHIC and the LHC, combined with what is now emerging as comparative data model analysis, will resolve that mystery. And what I'm sure is that Rolf Hagedorn, if he could sit here and see this, would be very pleased. Thank you.
Okay. Thank you, Bernd, for this talk. Thank you. You even managed to show new data. But that was there will be many questions I can see. Who wants to start? Otherwise, I start. The multiple component analysis you showed, I was surprised about one point. We normally think, and we have even models that work without bulk viscosity. So you naively would think that the uncertainties on any such analysis should be much larger for the bulk viscosity you extract than for the shear viscosity. However, when I looked at the envelope of these different models, they were of similar size. How comes?
Well, I think we don't really know the answer to that question yet. One of the drawbacks of such analysis is that it does not immediately point you to one particular observable that tells you why one quantity has that value.
I mean, what you saw is the functional shape they assumed was obviously a shape that peaked around TC and was vanishing almost everywhere else. As such, you expect that it has a very small implication for most of the accurate flow data that enter the analysis. And then you wonder naturally whether it's mainly the choice of the restricted functional shape the authors picked that leads to any constraint.
No, I think what it tells you is that in order to get good agreement with the data overall, the effective pressure near TC has to be lower than the equilibrium calculation tells you. In other words, that the breakup happens in a different way than equilibrium thermodynamics would suggest. And I don't think this is quite at the limit of cavitation, but it brings you closer to it. Now, you could probably trade that off by changing the equilibrium equation of state to reduce the pressure in that range, or the sound velocity.
You made this remark at the very beginning that, so clearly you replace pressure by an effective pressure that is pressure minus bulk viscosity times expansion scalar. Right. If that is, however, your interpretation, then you should see differences in systems that have different transverse expansion. So the test, yes, the experimental test of a cavitation would be that you read out from your last wave fit or whatever the three-dimensional expansion scalar, mm-hmm, and that you show that you are sensitive to the extra bit of bulk viscous pressure.
I mean, yeah, clearly this is the first attempt, and there is a lot more work to be done. But I think, I mean, the important thing that I take away from it is that sensitivities are actually there, and that with more work, we will first of all understand what exactly it is in the data that forces this, but also that ultimately may allow to combine, this is all based on lead, right? How to combine different systems, how to combine different beam energies in order to become sensitive not only to the to the quantities going into the simulation, but also to see to what extent the determination of them depends on particular assumptions of your model, right? I mean, that's clearly the beginning. And
yeah,
yeah. Almost to the same point. I have been puzzled by two results you presented. The one is that the bulk viscosity has this tremendous peak at around 180 MeV.
That is expected, yeah, on general grounds.
And the second is that then the shear viscosity ratio with entropy varies between RHIC and LHC. This is the largest variance which I have seen so far between, in the Quark-Gluon Plasma properties for the two systems. And mm-hmm, I don't see it in any other observable in actual fact. So there's a question, how come that the analysis produces such diverse value of the shear viscosity? I mean, I can't see where it comes from.
Well, it comes from the fact that the initial fluctuations are quite different at the different energies.
So it's assumption.
Now, there is a connection to the initial state, right? So if you would make an assumption that the initial state is the same in both, then you would also get a more similar shear viscosity. However, I think there is enough information in the multiple components of the flow that it is probably possible, but that hasn't been demonstrated, that it's probably possible to independently separate these two quantities from one another, right? At this point, this is, again, it's the first step that has been done, but I think there is reasonable belief that the data will be good enough to separate these two aspects from each other. But again, this is, I mean, the beginning at this stage. Mm-hmm. The bulk viscosity clearly was expected to have a peak in this range because it is connected with the deviation of the QCD equation of state from conformal behavior. And that peaks, according to the lattice, at 180 to 200 MeV.
Yes, but the largest deviation is where the interaction measure peaks, and this is not right where this peak in the entropy is. This is really the puzzle for me, because I would have shipped, if you produced it at 150 MeV or 160, it's shifted by 30 MeV and it's so peaked. So it's really not. The interaction measure measures the deviation, correct, yes, and right, you superpose interaction measure on top of the shear.
The parameterization makes use of the calculated interaction measure.
But from which year? Because that is really the problem. The old computation of Basabov and all was wrong.
I think it uses the Wuppertal data.
Okay, so Federico.
So maybe if you can go to 37, I think it is,
37.
which is where you show this multiplicity dependence. Now, I think that yes, here. So I think that this huge dynamic range of multiplicities for me is one of the most interesting features of doing physics at the LHC, in particular in the context of strangeness. Well, you know, when I worked for many years with Emanuele, after we discovered the enhancements, we tried many ways to switch them off. So we went low in energy, we went to more peripheral, but the enhancements stayed there. And now with the proton lead and even the proton-proton data, we can sort of dial in. And I think that this offers a unique opportunity to understand in more detail dynamically how the Strangeness enhancement sets up. And if you go to the next one, I think you have some comparison with canonical equilibrium, and I think that we should strive to go as precise as possible in these comparisons. Now,
that contains this parameter RC, right?
Right. Now, another way, of course, is gamma S. And one thing that, at least to describe the departure from grand canonical equilibrium. And one important observation actually is that the phi, we have measurements on the phi both in proton lead and in lead. And of course you do not expect any effect from canonical suppression for the phi, but still we see the same behavior for the phi going up from the low multiplicity values to the grand canonical, to the full equilibrium values.
Yeah, so I think this suggests that it is not, maybe there is a contribution from canonical suppression, but it's not all. And I think it would be very interesting to see someone like Jan, who has pioneered the dynamics of strangeness production.
Absolutely.
To see whether this can be understood.
Now, and okay, this is perhaps my personal bias, but I don't believe that canonical suppression explains any of this. Canonical suppression describes in the limit what we see. It works as long as you have equilibrium, and as long as you have equilibrium in a grand canonical system or in a more limited size system. If you are in equilibrium, then you can describe it with a few parameters, and these are the parameters that you extract from a canonical or grand canonical analysis. But dynamically, it doesn't tell us anything about what is happening.
That's right.
Actually, I wanted to mention that eta over S, of course, is a temperature-dependent parameter, and the initial temperature at LHC energy is higher than at RHIC energy. This eta over S is, of course, constant. In these calculations was not assumed to be temperature-dependent, so this is an average over the evolution in the Quark-Gluon plasma. And since we have a larger in the initial state eta over S at LHC, then the average can be different at RHIC than LHC. So this is for me a natural that there are different eta over S at LHC and RHIC, and it should be bigger at LHC than at RHIC in that case. I mean, this is what you see actually.
It's a natural expectation.
So this is natural expectations.
Whether it is quantitative agreeing with this, I don't know, right? I mean, it's this is what we like to know, and it is clear that data from one beam energy is not sufficient to resolve that. I think we'll like to see analysis like the one that Stefan and his students have done for several different energies, and clearly if it is a temperature-dependent effect, then the results from calculations and comparison with data at the new measurement that is going to happen in the next few weeks will be extremely interesting.
If I can, additional comment after Federico comment. I'm somehow surprised because that you really think that these canonical effects is not a physics, okay?
No, that's not what I said. What I said is as long as you are in equilibrium, you can describe your system with a few parameters, doing a canonical fit, which then becomes grand canonical when you are in
So
the
your
limit.
point is to understand how the system reaches
Right,
equilibrium. Okay, now
dynamically.
I understand. Okay, thank you very much. Now I understand. Okay.
I have actually a question on another figure you showed, because this tip-toe uranium data, at least I saw it the first time. I'm not sure whether it was shown in this form before. How accurate, so I mean, you have seen the analysis, you have seen the predictions presumably before. There was a long discussion of what could be said about the multiplicity distributions and the high multiplicity details of that distribution from different models. So on the one hand, I see this, but can you say how well do the models in describing really the uranium multiplicity distribution? And for instance, you know, I read X hard equals 0.13 for Glauber, but on the other hand, I think while there is a best value for Glauber to get a multiplicity distribution, if you ask about chi-square fits on a multiplicity distribution, you will find that this parameter alone simply doesn't do the job.
Right.
So,
yeah, I mean, the paper actually...
Qualitatively, it's of course very nice to see finally what one expects. But
so the paper does contain comparison with the models in the multiplicity distribution. I didn't bring the curves. They're not perfect. It turns out actually that maybe more difficult than gold, than uranium is gold. There are some uncertainties in the geometric shape of the gold nucleus that matter here. And I think there's clearly more work to do for the theorists on this one.
so this is PT integrated V2, huh?
Yes.
And were there hydro predictions, quote unquote, for that prior to data? Because
I don't know.
then the last question, did I miss this in Japan or was it not shown in Japan?
This, well, the data were shown, but not all the theory curves.
Okay.
And as a matter of fact, there was a considerable interaction with the referee on that paper to lead to that final version, apparently.
We had, so I think at that stage, if there are no questions specific to this talk, then we definitely thank first